Hi, everyone. Thanks for inviting me to speak today. I'm Kelsey Morgan from the National Institute of Science and Technology in Boulder, Colorado. And unlike the previous speakers in this series, I'm actually pretty new to the field of X-ray science. My background is in cryogenic microcalorimeter X-ray detectors. So today I'm going to talk about one particular type of cryogenic detector, the transition edge sensor, or TES. And I'll tell you about why TESs are starting to be more and more common at beamlines for X-ray and gamma ray science. So I'll start out by explaining what a TES is and how it works. And in particular, I want to focus on how a TES is different from other detectors that you might usually find in a beamline, and therefore why you might want to choose to use a TES for your experiment. Then I'll highlight a couple of TES spectrometers that are currently doing science in the field. And finally, I hope to get you excited about what sort of advances you can expect to see from these spectrometers in the near future. And the main reason that microcalorimeters detectors like the TES are appealing for X-ray science is that they are energy-dispersive detectors that achieve EV scale energy resolution. So you get a little bit of the best of both worlds. The efficiency is comparable to a typical energy-dispersive detector like STD. The TES is also inherently broadband, meaning that you can measure multiple spectral lines simultaneously. And the TES can achieve energy resolution of a few eV, which is closer to the performance of a wavelength dispersive instrument. But the efficiency is much higher, factors of 10 to 100 times or more. If you're interested in reading more about how the efficiency of a TES compares to wavelength dispersive instruments, I've listed a good example of a reference with some calculations here. The reason that the TES can get such good energy resolution is because a microcalorimeter measures heat, not free charge. That means that the energy resolution is not limited by statistical fluctuations in charge carriers that limit semiconductor-based detectors. Instead, the energy resolution is limited by thermal fluctuations between the sensor and its heat bath, which is kind of captured in this equation here. In order to achieve the best possible resolution, the calorimeter should have a very small heat capacity and it should be very cold. So we typically work at temperatures of order 100 millikelvin. Even then, the temperature change imparted by a single photon is very small, so we need a highly sensitive thermometer. And the transition edge sensor is going to provide that sensitive thermometer. To understand how a TES measures X-ray energy, we can look at this schematic of a generic microcalorimeter detector. It's got some heat capacity C, and it's going to sit at an equilibrium temperature T. When a photon with energy E is absorbed in the sensor, the temperature change of this block is going to change by an amount that's simply equal to E over C. The sensor also has a weak thermal link to a heat bath so that it can cool back to its equilibrium temperature and be ready to measure another photon. The time scale for this cooling is set by C over G, where the conductance G is the strength of this thermal link to the bath. To count more photons, we can increase the strength of this length. That shortens the duration of the X-ray pulse. However, faster signals do require more readout bandwidth, so there are trade-offs to be made between system complexity and speed. The TES itself is a thin film of superconducting material. At the temperature where the film transitions between its superconducting and normal resistive states, the resistance is a very steep function of temperature. Therefore, the TES works as a resistive thermometer. It converts a temperature change into an electrical signal that we can measure. We apply a voltage bias to the film so that at quiescence, the TES sits at a low point in this transition curve. Then, when a photon is absorbed, the temperature of the detector increases, so the TES resistance increases. That temperature change and consequently the resistance change is proportional to the energy of the photon. We read out that resistance as a change in the TES current, and the height of this current pulse is proportional to the energy of the original photon. The resistive transition has a finite width in temperature. So if the energy of an incoming photon causes a temperature change that's large enough to drive the TES into its normal state, the resistance versus temperature curve flattens and you start to lose sensitivity. So that sets what we call the saturation energy, which is the highest energy a given TES can measure with good energy resolution. It also means that there's a trade-off between sensitivity or energy resolution and energy range. So we have to match the heat capacity and the sharpness of this transition curve to accommodate the desired energy range. Another feature of the TES is that the energy resolution is roughly constant for all energies up to the saturation energy. So for X-ray science, the TES has two main strengths. First, they've demonstrated excellent energy resolution. The current state-of-the-art in TES resolution is EV scale for X-rays. Recent soft X-ray pixels have demonstrated resolutions better than 1 EV at a KeV. For gamma rays, resolutions of a few tens of EV are possible, all the way up to 100 KeV. So here I've just shown some examples of NIST-based results to date, and of course, we're always working on improving this resolution even further. The second strength of the TES is efficiency. At the individual sensor level, the light absorbing material can be matched to the incoming radiation. So for example, for X-rays, a thin layer of a high-Z material like gold or bismuth makes a great absorber, so the TES is nearly 100% efficient. And for higher energies, we can use materials like bulk tin. We can also increase the total efficiency of a spectrometer by making large arrays of sensors, and that's possible because TES readout can be multiplexed. That allows tens or hundreds of sensors to be read out with just a handful of readout lines. To make a TES, we use a thin bilayer made up of a superconductor, which is typically molybdenum, and a normal metal like copper or gold. The normal metal suppresses the intrinsic critical temperature of the molybdenum, and by varying the relative thickness of these two layers, we can tune that temperature. Remember that the lower the temperature, the better the energy resolution, but we also need to match the cryogenic system that's available. Next, to increase the absorption efficiency, a high-Z absorber can be added to the bilayer. And this entire structure is going to sit on top of a silicon nitride membrane that's going to provide the weak thermal length to the heat bath. Typical pixel sizes are in the hundreds of microns for X-rays, and they can be as big as millimeter scale for gamma rays. So since the individual sensors are small, the real power of a TES spectrometer comes from the ability to make arrays of hundreds, or in the future, thousands of sensors. The total collecting area of the spectrometer simply scales with the number of TES pixels in the array. The sensor arrays are packaged with custom-built readout electronics, and then they are installed in commercially available cryostats to make a complete spectrometer. So next, I'm going to walk through the process of using a TES array to make a measurement. So when you measure a sample with a TES spectrometer, you get 3 pieces of information about each X-ray that gets absorbed in the sensor: the energy of the photon, the time that it arrived, and the location of the TES pixel that was hit. Determining the time of arrival and the location are trivial, but converting the height of a current pulse to an energy takes a little bit more effort. So we do that by measuring a sample that produces a set of known X-ray energies to produce a calibration curve. So in this example, I've used my TES to measure a sample that contains some transition metals with very well measured K-alpha emission lines. And I can take these measured pulse heights to produce a calibration curve for my TES pixel. Now we can look at X-ray pulses from our science sample. They might look like these examples shown here. We can measure the height of this pulse in TES current units and then use our calibration curve to translate that pulse height into an X-ray energy. So in this way, each TES pixel in an array functions as an independent broadband energy-dispersive spectrometer. Remember that the TES measures the entire incoming spectrum with roughly constant resolution up to its saturation energy. So that means you can collect the spectra of multiple emission lines in the same measurement, like I'm showing in these examples of one of our soft X-ray sensors, measuring many emission lines between 0 and 1.2 keV, or these spectra here, which were collected with one of our hard X-ray pixels, collecting emission lines from about 4.5 all the way up to 8 keV simultaneously. So that makes a TES array a very versatile area detector. You can sum the signals from each pixel for higher statistics, for example, in an X-ray fluorescence measurement, or you can use the pixels individually. For example, each pixel would measure a different scattering angle in an X-ray scattering experiment. If you're interested in making measurements with the TES spectrometer, there are a few options that are available now. There are 2 spectrometers at SSRL beamlines 10.1 and 13.3. Both of those instruments have 220 pixel TES arrays that provide about 2 square millimeters of total collecting area, and they have about 1.5 EV energy resolution in the soft X-ray. Beamline 10.1 is optimized for partial fluorescence XAS and RIXS measurements. They have some pretty unique sample preparation capabilities, including the ability to measure frozen samples. Beamline 13.3 is optimized for scattering experiments. They've got a 4-cycle goniometer and a 3-axis sample positioner, as well as the ability to control sample temperature from about 24 to 320 Kelvin. Both of those instruments now accept general user proposals. If you're interested in using the TES at one of those beamlines, I'd recommend contacting the beamline scientists, and I've listed their names here. At 10.1, the main scientific disciplines are bioscience, catalysis, condensed matter, material science. For a good overview of the TES spectrometer's capabilities, I'd point you to this paper in RSI. And I just wanted to show a couple examples of RIXS planes that have been measured with this instrument. This plane on the right is a measurement of a 5 millimolar sample of aqueous ferrous cyanide. It was collected in about 5 hours of measurement. So this is a good demonstration that it's possible to measure very dilute samples in a reasonable amount of time thanks to the efficiency of the TES. This paper here actually also shows results on concentrations as low as half millimolar. And so far, the TES has been used to study quite a wide variety of materials, from catalytic and battery materials to carbon nanotubes. And I've listed some of those materials, some references for the studies here if you're interested in checking those out. At 13.3, the scientific focus is on condensed matter physics, energy, and material science. The experimental station is set up primarily for resonant soft X-ray scattering. And here's some data from an experiment performed with the TES where we were looking for scattering off of charge density wave order in a copper oxide high TC superconductor. The scattering signal of interest is very weak, and so these experiments are typically performed with an energy integrating detector. But the signal that you're looking for is dwarfed by a large background of L-alpha fluorescence. So in these middle plots on the right here, you can see what this measurement looks like if you're using an energy integrating detector. And the signal that you're looking for is this tiny bump on top of a very, very large background. But with the TES, having energy resolution allows you to separate the large fluorescence peak from the much weaker scattering signals that you're actually interested in measuring. So in this example, the TES provided a statistical advantage of about 5 to 10 times over an energy integrating detector. If you're interested in learning more, I've listed a reference here that will tell you more about both the CDW experiment, the experimental station setup, and the TES spectrometer. In addition to these beamline instruments, we also have some pretty unique capabilities available at NIST in Boulder, using a tabletop spectrometer that we've built to do time-resolved X-ray emission and absorption spectroscopy. In this experiment, we use a pulsed laser to excite a sample dissolved in a water jet using a short optical pulse. That same laser is used to strike another jet, which creates a plasma that produces broadband Bremsstrahlung radiation. That emission gets focused by a polycapillary X-ray optic onto the sample. And that X-ray probe pulse is very short and only lasts for a couple of picoseconds. And we can vary the time delay between the pump and the probe with few picosecond precision. The X-rays that get emitted by the sample are then measured by a 256 pixel TES array that has energy resolution of a few eV and works up to around 10 keV. So this is an example of a measurement that was made with this system. Materials with spin crossover complexes like iron tris by pyridine are of interest for applications like solar cells and memory storage. And an important property of spin crossover materials is the lifetime of the high spin state. So the pump laser is used to excite the iron tris, which then decays exponentially back to its low spin ground state. And we can measure that time evolution by making measurements of the K-alpha and K-beta spectral features with our TES. And we can do that for several different time delays between the pump and the X-ray probe. Our data show a fast rise of the high spin fraction at time 0, followed by an exponential decay of the high spin state that has a time constant that we measure to be about 570 picoseconds. That time constant is consistent with previously reported data that was collected from a synchrotron, but that synchrotron measurement required 10 to the 4th more photons delivered to the sample, which really demonstrates the collection efficiency of the TESs. This measurement also showed, thanks to this fast rising edge of the high spin fraction, The time resolution of our system is better than about 6 picoseconds. That's 10 times better than what's typically achievable at synchrotrons that are capable of time-resolved measurements. We can perform emission or absorption measurements by repositioning the spectrometer. The system can also be used for static measurements as well. So at the moment, we don't have a formal system for applying to use this instrument, but we're always looking for collaborators. So please do contact us if you're interested. And I've listed some of the specifications for the system here. So for the last part of the talk, I'm going to give you a little bit of an idea of what we see as being the future of TES spectrometers at beamlines and light sources. We think there's still a lot of room to expand the capability of the spectrometers, and one way to do that is by improving the sensors themselves. We can do that by finding new and better materials and by improving our understanding of the physics of the superconducting transition. Later this year, we plan to deliver a new TES array to the spectrometer at SSRL beamline 10.1. The individual TES pixels in that array will be much larger. That'll give the total array an increase of about a factor of 7 in solid angle. Even with those bigger pixels, we also expect an improvement in energy resolution. Prototype devices have achieved energy resolution better than 1 eV for energies below a keV. So we're excited to deliver that new array. We think it's really going to improve the scientific capability of that instrument. In the future, we also want to cover more solid angle by making arrays with more TES pixels. That's going to require both improvements in multiplexing technology, allowing us to read out the sensors more efficiently, and also an array and electronics packaging, which will allow us to pack more pixels into a smaller footprint. Our current generations of instruments have 256 pixel arrays. So this picture here shows what the current detector package looks like. The array of sensors is at the top, and it's surrounded by the multiplexing readout circuitry around the sides. So we're currently developing a miniaturized version of this object that's going to allow us to place 1,000 pixels in their accompanying multiplexer chips in roughly the same space. With new microwave multiplexing techniques and this new packaging, we expect to be able to read out arrays of up to about 10,000 pixels. Making the design more modular in this way has a couple of advantages. For one thing, it makes fabricating and screening all of the detector and readout chips much easier. And it also allows for future systems to be upgraded because we can simply tile more of these objects together to make a larger array. So on a longer time scale, we're working to develop an even more compact version of this packaging and use advanced hybrid multiplexing techniques we hope will allow us to read out arrays of as many as 100,000 pixels. Another way to increase throughput is to shorten the duration of the X-ray pulses. That allows each sensor in an array to count more photons per second. In the current instrument, the sensors have pulse decay time constants that range from a few hundred microseconds to a few milliseconds. And that gives us count rate capabilities of tens or hundreds of photons per second. However, we've already demonstrated that it's possible to use advanced fabrication techniques to shorten the thermal time constant of the sensors. And we've already demonstrated readout of the sensor with a 30 microsecond fall time constant. And we expect that time constants as short as 10 microseconds are feasible. That would give us count rates for an individual sensor of thousands of counts per second. So finally, I want to just highlight a few upcoming projects that might be of interest to the X-ray science community. We are collaborating with Los Alamos National Laboratory to build a TES array for use with a scanning electron microscope. This isn't going to be a broadly available instrument, but it does represent one of our first forays into the tender X-ray regime between 2 and 3 keV. There are also a couple of instruments in the works that will operate in hard X-ray regimes that we've not previously focused on. For example, a collaboration with Riken and Tokyo Metropolitan University in Japan will use 50 keV X-rays to study quantum electrodynamics. And Argonne National Lab is leading a project to develop a TES spectrometer for X-rays up to 20 keV. That instrument should be available for use at the APS after its upgrade. We'll be delivering another soft X-ray spectrometer to a NIST-owned beamline at NSLS2. That instrument will have similar performance to the SSRL instruments. We're also building an instrument for a beamline at Bessie in Berlin. That's an exciting project because it will have our best ever energy resolution that we've delivered for the soft X-ray. There are more TES spectrometers in the works, and there's many more doing experiments around the world that I've got time to talk about today. So I'd encourage you to check out this review paper, which really gives a good overview of the many instruments that are already in the field. And I'll just reiterate, we're always looking for new opportunities to collaborate on instruments or measurements, and we hope we can continue to provide new capabilities to the X-ray science community in the future. So thank you all for giving me the opportunity to present here today. And I hope you've are excited about the possibility of doing X-ray science with transition-ed sensors in the future.